Hey guys, in this video we're going to introduce a new class of functions called quadratic functions. And when I say class of functions, I mean things that we've looked at like linear functions, exponentials, polynomials, and now quadratic is its own new thing. Now interestingly enough, since we've talked about polynomials, you've actually heard the word quadratic before, and you're going to find out that there is a connection between them, namely that a quadratic is just a specific type of polynomial. But we're going to look at the graphs of these quadratic functions and identify some key features such as the vertex, y-intercept, axis of symmetry, and roots. And we're going to be able to look at either the equation or graph of a function and determine if it is quadratic. So let's start off with this. What is a quadratic? Well, it's just any polynomial, so all the polynomial rules apply here, any polynomial that has a degree of 2. And here I've given you 3 examples, and you can see all 3 of these are polynomials. I've got a monomial, a binomial, and a trinomial. And all of them are of degree 2, that is the largest exponent on any variable is 2. And what we're going to do now is we're going to look at the graph of these. And what I want you doing is thinking about what they all have in common. So here's the graph of y equals x squared. This is a particularly important equation because this is what's called the parent function of quadratics. And the reason it's called the parent function is that this is the simplest version of a quadratic. And just by changing this equation, y equals x squared, we can create the equation and graph of any quadratic. But you can take a look at it. This red line right here is the shape made by the graph of y equals x squared. And we can look at y equals negative 0.5 x squared minus 5x. You can see there's a difference in that this is now upside down compared to the other one, but you can still see a similar shape. And we have y equals 2x squared plus 3x plus 9. And you can see now that, again, it's a different graph. The locations are different, and yet there is something that's the same. See if you can identify what that is. So the thing that all of those had in common is this U shape. Doesn't matter if it's like this or if it's upside down. They all had that particular U shape, and that shape is called a parabola. And so parabola is the name of the shape of a quadratic function. And we're going to be looking at these parabolas mostly in an abstract mathematical sense, but I don't want to leave you with the idea that that's all they're good for, because the parabola happens, well, everywhere. So let's look at some natural examples of this. What this is a film of somebody shooting a basket, and they've stopped the film and like spliced out the path of the ball as it travels. And so there's naturally a question that this makes you want to ask, which is, does it go in? And the way we would find out is we would trace the path of the ball and see if that path, wow, good job tracing that, Mr. Kelly, see if the path of that ball leads into the basket. And when we trace out that path mathematically, what it creates is, of course, a parabola, or else why would I give you this example? Anything that is thrown on the Earth's surface such that air doesn't catch it and change its path a lot, anything thrown on the Earth's surface will travel in a parabola. So we can see, this basketball, I'll do this in red so you can see it against the sky. This basketball travels along that path. Sometimes when we throw things, it travels in a much more gradual parabola, or if we throw it straight up, it could be more dramatic like this. But every time you throw an object under the Earth's gravity, you will always get a parabola, provided the air doesn't catch it and do something else with it. And so you've seen a parabola nearly every single day of your life without necessarily understanding that that was a mathematical object that you'd be studying later. Very interesting stuff. You also see it quite a bit in architecture. And in architecture, these parabolas are called arches, And here you can see them on a Roman aqueduct that is over 1,000 years old. So this thing is really, really holding up well. But when you have these arches, if you're looking at it from an engineering or architecture standpoint, what happens is that any force you put on the top of the arch gets transmitted down the arch at kind of an angle. And what that does to the bricks or the stones that make up the arch is it compresses them together and makes them really, really solid. So that once you have the arch constructed and you've got some weight on top of it, it becomes well nigh indestructible, making it really, really great for building. It also channels all the force down into these pillars that you see here, and so the force goes downward and just a little bit outward, and that helps put the force of the structure wherever you want it. So all of this weight right here is going into these areas right there, and you can see we've got the big stone supports. This one is built right into the hillside so that all that weight is supported going outward and all the weight supported by the ground going downward. And at least you think that this is just old architecture that uses this. Here's an example that is pretty prominent still in Paris, France. The Eiffel Tower, this is the bottom. You can see this arch, the parabola shape right there, and that's taking the weight of the entire tower and putting it down through these legs and outward into the ground that way. And so the force is channeled somewhere that can take it, like the ground, and it supports the rest of the structure. Another neat place you see these are satellite dishes, which are becoming less common but used to be pretty much everywhere. Is if you trace out the bottom of a satellite dish, that shape is a parabola, and so everywhere around that is a parabola, and it takes advantage of this really fantastic property that parabolas have, and that they have something called a focus. And so what happens if you take, say, radio waves from a satellite, or basically any kind of wave for that matter? As it travels into the dish, it will reflect off the surface of the parabola, and every bit of it ends up right at the focus. So it doesn't matter what direction these waves come in from, they all bounce right to the focus. And so this dish serves to collect all of those rays, say like from a satellite TV station. It collects those rays and focuses them at the focus of the parabola, where we put a sensor that can pick up and detect the signal. So a really fantastic use of that. Final example, this one's probably not obvious just from looking at it, but this is the path of a comet that traveled by the Earth in 1974. This little bright spot here in the middle is the Sun, and this blue spot here is the Earth, and the red is the path of the comet. And you probably recognize that path. Under the influence of the Sun's gravity, this comet traveled in a path that was a parabola around the Sun, and you can see those places where it got close to the Earth and put on quite a show for folks. So those are some places where you can see parabolas in real life. Now let's talk about them in an abstract mathematical way, because hey, this is math class, right? So we have 4 parts of a parabola we're going to look for: the vertex, y-intercept, roots, which is a name for the x-intercepts, and what's called the axis of symmetry. We're going to start with the vertex, which is arguably the most important feature of the parabola. Everything else is determined by this. So the vertex is the highest or lowest point on the parabola. So in this case, I've got a parabola that is U-shaped, and so the vertex is going to be that lowest point. Let me switch over and do this in blue so it's a little more obvious. But it's the lowest point on that parabola. And we give that location as an ordered pair. So I'll give its x-coordinate, which is 1, and its y-coordinate, which is -4. And so I would say the vertex of this parabola is at 1, -4. If it was an upside down parabola, we'd be looking for the highest point, and we actually have names for that. In this case, when we have a lowest point, like this, we also call that the minimum of the function. And if I ask you for the minimum of a quadratic, what I'm really looking for is just the y value, because that'll be the lowest y value on the entire graph. And so in this case, the minimum of the function is -4. So let's look at a situation where we have a maximum. Here we have that upside down U shape. The vertex is going to be that highest point. In this case, it is at -2, 1. And so at -2, 1, we have our vertex, and this vertex is going to be a maximum. It is the highest point on there. And if I ask you what is the maximum of this, you're welcome to give me just the y value of the vertex. I just want to know what's the highest point it goes to. So our maximum would be 1. So that's the vertex. Just our highest or lowest point. Give it as an ordered pair unless I ask you for a minimum or maximum. We can also talk about the y-intercept, and this one is the same y-intercept we've talked about since we first started with linear functions. You find the y-axis, that's the one that goes up and down, so there's the y-axis and the x-axis. Find where the graph crosses on the y-axis, and that is your y-intercept. So in this case, the y-intercept is -3. All you have to do is give the y-coordinate. It's not necessarily wrong if you want to give the whole thing as an ordered pair and say that it is at 0, -3. Note that at the y-intercept, the x value will always be 0. Now, the y-intercept is where it hits the y-axis. The next thing we're going to talk about are what are called roots. And roots are x-intercepts. That is, where does the graph touch the x-axis? And you can see that this parabola has not just one, but 2 x-intercepts. So the x-intercepts for this one would be at -1 and at 3. And just like with the y-intercepts, if we really want to, we can write those as full-out ordered pairs. There's certainly nothing wrong with that. But you can also just give the x-coordinate because we know the y-coordinate is going to be 0. Now with a parabola, you can have one of 3 situations. Like this parabola, you could have 2 roots, but there's also situations where you would only have 1 root. And that will happen when the root and the vertex are at the same place. So here, our vertex is at 2, 0, and our root, our x-intercept, is also at 2, 0. So when the root and the vertex are the same, you will only have 1 root for the parabola. And then our third and final situation is this. The roots are where it crosses the x-axis. You might have a parabola that doesn't cross at all. And so we would say that this has no real roots. Now you might ask why we say no real roots. The reason is even though this has no real roots, it does have something called imaginary roots that you will talk about in Algebra 2. We're not going to go into depth in that other than to tell you that they exist and say that when you tell me there are no roots, please say no real roots. Let's tell the whole story as opposed to just part of it. Final situation we need to look at is what's called the axis of symmetry. And the axis of symmetry is just a line through the vertex of the parabola that divides the parabola into 2 symmetrical halves. So I've got this line right here. And what I want you to notice is if I put this line through the vertex of the function, it divides this graph into 2 sections. This section right here and this section right here. And they're exactly mirror images of each other. And that's what's known as symmetry. And we can also look at it as a distance argument. If I take this point right here and I look at the 2 points there and there, I go over 2 spaces to get to this one. I go over 2 spaces to get to this one. They're the same distance away from that line. If I look right here and right here, the distance from that point to there is 1. The distance from that point to there is 1. And so this line cuts the parabola into 2 mirror image halves. So that's our axis of symmetry. We want to write an equation for the axis of symmetry, and here's how we do it. It's always an equation of the form x equals, and then whatever the x-coordinate of the vertex is. So in this case, 1. And if you'll recall, x equals is the form of a vertical line, which is what we have right here. So if I ask you what the axis of symmetry is, I'm looking for an equation of the form x equals some number, and that number will be the x-coordinate of the vertex. So let's look at another one. Here I have one of those upside down parabolas. The axis of symmetry will be through the vertex right there. That divides the parabola into 2 distinct halves. My vertex was at -2, 1. So my equation will be, for the axis of symmetry, will be x equals -2. And that would be the equation for that line. So to recap, quadratic's just second-degree polynomials. We've touched on this before. Now we're going to go into detail. When you graph a second-degree polynomial, you get a shape that's called a parabola. It looks like a U. The vertex is the highest or lowest point. If it's a highest point, we call it a maximum. Lowest point is called a minimum. The y-intercept is where it crosses the y-axis. The roots, or x-intercept, is where it crosses the x-axis. And for the roots, all these quadratic functions can have 0, 1, or 2 roots. All 3 of those are possibilities. And then we have the axis of symmetry with the equation x equals some number, where that number is the x-coordinate of the vertex, and it divides it perfectly in half. Study well, my friends, and good luck.